Okay, we're going to look at Doppler effect, and we're going to look at the situation of Doppler effect with no wind present. So in order to do that, we can look at if the source is moving and or the listener is moving. In order to use that, we're going to need this equation. So this equation tells us the frequency the listener observes is equal to the frequency of the source emitting it times this term. Now, this term has a few parts to it. Now, one of those parts is this V, and that V stands for the speed of sound. 344 meters per second is the value we are going to use. And so it's just the speed. It doesn't care about direction. But notice that both of these, the velocity of the listener and the velocity of the source, have arrows. So we do care about their directions. So these are vectors, so they do have direction. So now, the next important thing is how do we determine their direction? So this is what we'll do. Every time we start one of these problems, we're going to start with two dots, an L and an S. L being the listener, S being the source. And we're going to draw an arrow with the positive direction labeled from L to S. This will be our positive direction. Now we can look and say, okay, if the source is moving away from the listener, it will have a positive velocity. If the source is moving toward the listener, it will have a negative velocity. If the listener is moving toward the source, it will have a positive. If the listener is moving away, it will have a negative. And so we can use this convention to figure out what is the frequency the listener is going to hear. Now, the one rule that you need to remember is if the two objects are getting closer together, the listener and the source, as long as they are getting closer together, the observed frequency, the one the listener hears, is going to be greater than the one the source emits. If it's the other way, if the two objects are getting further apart, the listener is going to observe a lower frequency than that of the source emitting. Now, over here I have a graph, and so if they're getting closer, you should hear a higher constant frequency. And then as it passes you, it should switch from high to low. And just as it's right next to you, it will have the actual frequency that the source is emitting. Now, this slope, that's depending on how close it comes to you. So it passes a ways away from you, this slope is more shallow. If it passes very close to you, this slope will be sharper. Okay? Now, there's a second thing going on here. As the object gets closer to you, the intensity goes higher. And then as it goes away from you, the intensity goes lower. So some people might think, when they're listening, that that frequency is actually increasing as it approaches. No, you're just hearing a higher intensity. That frequency is staying the same. Now, there is one other influencing factor why people might think that the frequency as it approaches is increasing, and that is because in most cases, there's a mixture of frequencies. Say as a car comes toward you, there's a mixture of frequencies you're hearing. And there's something called sound attenuation. And attenuation is proportional to the frequency squared, meaning when a car is very far away from you, the higher frequencies drown out before they make it to you. So you're hearing a lower overall frequency group than if the car was close to you. But if we think about a single frequency, which is what our equation is set up to do, that single frequency will have a higher constant value and then drop to a lower constant value. So the next thing we want to do is we want to do some examples. We're going to do one where we have just a moving or just a stationary, and then we're going to do one where there's actually an echo. What happens when that sound bounces off? So let's set up those example problems. All right, so now we have our two example problems set up. The first one, we're going to have a train traveling at 15 meters per second, emitting 400 hertz. And we want to know what a stationary observer standing on the side of the tracks is going to hear as that train approaches at 15 meters per second. Our second example is we have a fire truck racing to a fire. The siren is on. The fire truck is going 30 meters per second, has a 1200 hertz siren, and it's catching up to a 20 meter per second box truck. And what's going to happen is that sound from that fire truck is going to hit the back of that truck, reflect off, and I want to hear what is the fireman hearing the reflected sound frequency to be. All right. So as we do with these, the first step is we need to draw two dots, an L and an S. And so here we go. So I have my S here. That is my source. I have my L over here. That is my listener. L to S is my positive direction. And so that means the train, the velocity of the source, is moving at negative 15 meters per second, where the velocity of the listener is 0. At this point, we can just plug it into our equation that we had from before, where the frequency the listener observes is equal to the frequency of the source, 400, times the speed of sound, 344, plus the velocity of the listener, which is 0, divided by 344, plus the velocity of the train, which is negative 15. Now these two objects are getting closer together, so we should hear a higher frequency than is being emitted. And when we plug this into our calculator, we find out that the observed frequency is 418 hertz, which is a little bit higher. And you can imagine the faster that train goes, the larger this shift in frequency. Now for the reflection or the echo situation. Now this one's a little more involved because it's two steps. You have to send the sound out and then bring the sound back. So it's going to be in two steps. So the first one is I have the source, which is the fire truck, and I have the listener, which is the back of the truck, even though in the end, the fireman on the fire truck is the listener. But we first have to get the sound to reflect back. L to S is our positive direction. So we see that the velocity of the source is going to be negative 30 meters per second, and the velocity of the listener is going to be negative 20 meters per second. Now what's going to happen after that is that sound is going to be reflected. So we are going to have a frequency of the listener here. That now becomes the frequency of the source. The sound is reflected back with whatever frequency it hits that truck with, it's now reflected back. And so now the truck is the source and the fireman is the listener. And so L to S is my positive direction. And so now I see that the fire truck has a velocity of positive 30 meters per second and the truck has a velocity of positive 20 meters per second. And so this is our link between these two problems. Is we're going to use the frequency emitted here to calculate what's observed by the truck, use that as my reflected sound source, and then observe what's listened by the truck. So let's set that up. So this is how it's going to look in our equation. So the frequency of the listener, that's this one. Maybe I'll label this listener 1, and we'll label these 2's down here, is going to be equal to the frequency of the source, 1, times the speed of sound, 344. This was 1200, I could put that in. 344 plus the velocity of the listener, which was negative 20, all divided by 344 plus a negative 30 for the velocity of the truck. This all then gets put in down below. So now I have the frequency the listener on the fire truck observes is going to be equal to all of this, which when we plug that in our calculators, we get 1238, which is reasonable that we should hear a higher frequency because the two objects are getting closer together. And then I need to multiply it by my information from down here. So 344 plus the velocity of the listener, which is 30, divided by 344 plus the velocity of my source, which was 20. And I put that all together and I find that the fire truck observes an echo that has a frequency of 1272 hertz. Now an interesting thing you can imagine now is, all right, I have this frequency that I'm hearing reflected off that truck, but there's also the direct frequency of 1200 hertz that I'm hearing from my fire engine. And so there's going to be a beat frequency produced between 1272 and 1200, which would be 72 hertz. Kind of an interesting effect from echoes.